Howdy folks, Mr. Holdeman here. Hopefully you are fresh off the heels of the combined gas law practice problems with Mr. Lackey, otherwise not sure how you got here. But today we are talking about the ideal gas law. So we're going to add a couple things to what you already know. First, what is an ideal gas? So glad you asked. An ideal gas is one that behaves exactly as we would predict, which is nice because then we can put it in an equation. So when we calculate the before conditions with pressure, volume, and temperature, and then change something, we want to make sure that what we get out of that is exactly like what would happen in the real world, a real gas. Most real gases are ideal gases. There are a few exceptions. But the law we discussed today and the gases that we discussed today apply to any gases that behave ideally. So any gas, basically, that we're talking about, an ideal gas. What is an ideal gas? Well, we are in the midst of this quarantine, and in COVID-19, we are trying to stay away from other people. So an ideal gas is exactly like that. Let's say you go to the supermarket. You're in a line, maybe you see the lines on the floor that they put in to keep people distanced from each other, 6 feet away, something like that. You see the guy down at the bottom right who made his own little UFO thing, just keep 6 feet away from other people. That's fantastic. But the best things, gases behave like the two people things mascot on the left. Don't come over by me. Gases like to stay as far away from each other as possible. Bonus points if you know what that reference on the left is from. Mr. Lackey will appreciate that as well. So a couple more pictures of that, but a little more on gases. Gases work the same way that these pictures do. So they spread out to fill the volume of their container. They'll take up whatever room they're in, but they'll spread out as much as possible in that container. And the size of the particles does not matter. It doesn't affect how far they are from each other because gases are mostly empty space. So that would be like if we, at the bottom, we see a picture at the White House staff room. The people, it would be like putting a different sized person in each chair. It wouldn't really affect it because there'd still be the same number of seats. They would still be as far away from each other as possible. So you took a look at pressure, volume, and temperature with the combined gas law, but we haven't talked about particles. So we're going to add those in just a bit. But first, we need to review our types of systems because we looked at pressure, volume, and temperature, but that was in an isolated system. So to review, remember that an open system is one where air enters or exits the system. Number of particles can change. A closed system is one where air does not enter or exit the system, so the number of particles stays constant. So far, we have only looked at closed systems because particles was not a factor in any of those equations. This is kind of like when we talked about energy and an open and closed system with energy. Does energy leave the system or enter the system? Well, in that case, it was an open system because we had energy going in or out. In this case, we're mostly talking about closed systems, but so that you get the idea, let's review a couple of examples. So this would be a good time to pause if you want to look through these, write down the 6 examples and see whether it's an open or closed system, or follow along. So we're going to look at the item in bold as the system. So number 1, car tire. Car tire as the car moves along the road. So the car tire itself, hopefully, is a closed system. Hopefully we're not getting any air in or losing any air unless you have nail through your tire. Number 2, fire extinguisher that is actively spraying. Fire extinguisher itself losing air particles, that is an open system. Balloon as it is being inflated, similar to the fire extinguisher, except kind of the opposite direction. So it is adding air particles, therefore it is an open system. Number 4, a bike tire as a pump is used to fill it. The bike tire is being filled, therefore it's an open system. Propane tank that is cooling outside in the winter, we assume that it's closed, and even though energy is leaving, we don't have particles leaving, so that's a closed system. And last one, a tide balloon that is heated up slowly. We'll see a couple of cool examples of this, where the balloon expands as it's heated up, but not because it's increasing particles. This is a closed system. No air is getting into it. So that's what we're talking about. We're talking about air in the system, not energy. Once again, we looked at pressure, volume, and temperature for a given amount of gas. So if we only focus on one side of that equation, pressure, volume, and temperature, we know we can manipulate those variables and do anything we want with them. So that stays the same. Pressure, volume, and temperature. For a closed system, because we're not adding anything in, this relationship stays constant. It does not change. So the equation looks like that. PV over T equals a constant. We just kind of ignore the other half of the equation because we're only working with these three variables. But what if, we've been talking about open systems, what if we add in particles? What does that do to it? So you remember this guy? Oh yeah, a real looker. That is Avogadro. So Avogadro, if you remember the TED video that we watched, he did his work on gases to come up with the idea of the mole. So we have Avogadro's principle that we can add to the equation that we just looked at. And it relates to two things at the top of the screen, particles and volume. So Avogadro's principle says that equal volumes of a gas at the same temperature and same pressure contain an equal number of particles, or he measured in moles. So, ladies and gentlemen, moles are back, but it's going to be a little bit easier this time, so don't worry too much about it. Because we're not going to count the particles individually, we're going to count them in moles. So there's our relationship. V1 over N1 is V2 over N2. That just says the exact same thing. If we increase the number of moles, we also increase the volume, just like blowing up a balloon. So if we take a look at this, we've got three different gases. So carbon dioxide, helium, and oxygen. And we're going to tell you that regardless of particle size, we have the same number of particles at the same pressure, volume, and temperature. So each of these canisters has the same volume, has the same pressure, and is at the same temperature. And if we look at each little, pretend that each little circle is our sample, same size sample, we have the same number of particles. So 5 carbon dioxide particles, 5 helium particles, and 5 oxygen particles. Again, just like that picture we saw of the press room, they take up the same amount of space. They just fill up whatever container is there. So with the combined gas law, we're going to add this in. Because volume and particles are directly related, we can add particles to the equation. And you see this N right there. That is how we're going to, that's the variable that we're going to put into the equation. N is the number of particles, or the number of moles. And there it is. PV over NT is equal to our constant. So see, it has the same relationship, V up top and N down at the bottom. So we just put it in down at the bottom, and this is our relationship. This is the ideal gas law. PV over NT is equal to some constant, stays constant, because we are not changing the system. So if we calculate this number, this R value, this constant, it would be the same for any gas, same number. And because we know all gases behave the same under the same temperature, pressure, and volume, because they're mostly empty space, when we calculate it, we get the ideal gas constant. Ideal gas law, ideal gas constant, and that constant is given the variable of R, capital R. We've got two values for this. We are going to do some calculations with this, so it's good to have numbers for this. This is one that doesn't change. It's a constant. So R is equal to 0.0821. That is if we're using atmospheres for pressure. So what we want to do is check the pressure, check the units that we're using for pressure. And if it's in atmospheres, we're going to use this value for R. Because we want the units to match, we want the units to cancel, so we need to use the right value. If we are using kPa, that's kilopascals, for pressure, then we're going to use the number R equals 8.314. You'll get pretty used to using both of these. The only thing you need to check, atmospheres or kPa for pressure. We're always measuring volume and temperature in moles using the same units, so pressure is the only one that changes. So what is the ideal gas law? If we put it into words, because we just came up with an equation that tells us what the gas law is. If you just remember that, pretty good to go. But in words, the gas law states that any gases under equal temperature, pressure, and volume will have an equal number of particles and produce equal R values. So it is the constant, and then if we change any of those things, obviously, it'll all be the same for all gases. That's it. So, what did we learn? Gases behave ideally, just like you in quarantine, trying to social distance, stay as far away from each other as possible. We learned Avogadro's principle, so volume and the number of particles are directly related. When we add particles into the combined gas law, so we put the N in the combined gas law, we call it the ideal gas law because they form a constant ratio. The ratio of variables, pressure, volume, particles, and temperature is a constant. So all of those give us the ideal gas law. We're going to do a few calculations with this in just a bit, so you will get very used to using R values in that equation. If you have any questions, let us know.